Welcome everybody. I'm going to talk about artificial intelligence today. Not about machine learning, not about neural nets, not about random forests and that kind of things, but about planning optimization, something I would consider more interesting than machine learning. Why? Machine learning is quite good for image recognition, voice recognition, and that kind of things. But human beings are actually quite good at that too. Human beings are very bad at planning and scheduling. And with the constraint solving optimization algorithms, we can actually do a much better job than what humans can do. So I'm going to talk to you how we can do that. I'm going to implement it on Quarkus, and I'll do some live coding to show that. And I'm going to use that using Optaplanner, which is an open source constraint solver that I started 15 years ago, back then as a hobby. But today it's used all across the globe in Fortune 500 companies, governments, ranging to startups and non-profits and so forth. So let's get started. So this is the application we'll build. So basically, we're going to assign, as it's an example application, we're going to assign lessons to rooms and to time slots. And when we click the solve button over here on the top left, then our AI algorithms will actually assign these lessons for us. So this is the use case, just so you guys understand. We have a number of lessons here you can see on the side: math, chemistry, French, history. And these are taught by different people. For example, Turing gives math, but Marie Curie gives teaches both chemistry and French. And then we have a number of rooms, room A and B, and we have a number of time slots in which we can assign these lessons. But you can see there's a number of constraints in there, planning difficulties in there. For example, both math and chemistry are taught to the 9th grade, to the same group of students, so they cannot be so they cannot happen at the same time. Chemistry and French are both taught by the same teacher. Again, they cannot happen at the same time. And French and history are also taught to the same students, to the 10th grade. So you can see we need to make sure that we abide by these hard constraints. These are actually hard constraints. So what we're going to do is we're going to give this to our AI engine, Optaplanner. We're going to do that on the Quarkus platform, as I've explained earlier. And then we're going to get a solution. And then for this very simple case, this is the solution, right? Now you might think this is quite easy to do. Well, it is if you only have to assign 4 lessons. If you have to assign 400 lessons, and you have 10 rooms, 50 time slots, the number of combinations is mind-boggling. It's not billions. It's billions of billions of billions of billions of possible combinations. And you need to find the best one or the near optimal ones. And this is where a constraint solver comes into play. So, okay, we can solve better schedules for schools. Like you remember when you went to school, those schedules weren't that optimal. But are there other planning problems for other kinds of businesses that we could solve this way too? And we can. So, for example, there's the employee rostering problem when we need to assign any kind of employees that don't work 9 to 5. So, for example, nurses, security guards, and so forth. And then we need to assign these people, these employees, to a number of shifts, like morning shifts. Here's a morning shift going from 6 till 2. Afternoon shifts, night shifts, and so forth. And again, there's a number of constraints we need to take into account, like make sure that people have the right skill. For example, this shift requires a nurse skill, so we need to make sure we assign it to a nurse, right? That we don't give people too many shifts per day, that we abide by their contracts and their labor laws. And there's soft constraints. One of them, I won't go through all of them, but one of the most important soft constraints is the day off requests. If, for example, one of these nurses says, I like to be free on Friday evenings, so I can go out, or I want to be free Wednesday afternoon, so I can take care of my grandchildren, then we want to abide by, we want to make sure that we deliver a schedule that actually does that. And by using optimization algorithms, we can actually fulfill the wishes of these employees far, far better, about 50% better than traditional algorithms or human-made plans, actually. And that's what we see most of the time. But the real moneymaker is the real change is the real difference is vehicle routing. So what do we need to do in vehicle routing? We have a number of delivery locations or locations where we need to go to, for example, to install cable or to do maintenance on something. And we need to figure out in which order our vehicles will go to these locations. And so we need to find the optimal route, a route where we do a number of constraints. For example, we make sure that we don't assign too much work to one particular vehicle. This could be, for example, if they're going to delivery locations because they can only carry 20 tons of freight or something like that. Could also be because they can only work 8 hours in a day if they're, for example, telco people installing cable and things like that. And then, of course, we have a number of soft constraints, and the major soft constraint in this case is to minimize the driving time. Because driving time is bad for everybody. It's bad for the company, of course, because that means they can do less work on the same day. But it's also bad for the environment because you spend more fuel. And so we've actually implemented this with a major, in a major case in the US for over 60,000 vehicles. And what we've seen is that they, year over year, they reduced their driving time by 25%. They were expecting 1%, right? Because they thought our human planners are really good at this. But actually, well, by optimizing this with algorithms, in combination, of course, with the knowledge from the human planners, and which gets still tweaked on a daily basis, they actually reduced their driving time by 25% year over year. That made a difference of hundreds of millions of dollars a year, and that also made a difference of tens of millions of, more than 10 million kilograms of CO2 emissions. That was the profit of doing this. And there's a downside, of course. You first have to implement everything and put it in production before you can see impacts like this. But another case is maintenance scheduling. So in maintenance scheduling, we need to assign a number of maintenance jobs. So for example, here it's about road maintenance. We have uptown street road maintenance, uptown bridge road maintenance, forest maintenance, and so forth. And we need to decide which crew does which job at which time. And of course, these jobs take more than one date, so we can start at any date, but once they start a job, they need to finish it. Now, each of these jobs has a ready date. That means you cannot start that maintenance job before that date, and has a due date, which means it needs to be finished before the due date. So you do have some room per job and when it can start, but not all. You cannot just use any date. So, and of course, one crew can only do one job per day. So again, you give it to Optoplanner, or you give it, right, and or another constraint solver, I would argue, and then you get a solution like this, right? And so the interesting thing is here we decided that crew A does the uptown street on the 1st of November, and then crew B actually starts with a day of doing nothing. Now you would argue that that doesn't seem logical because it could actually start the yellow job on the first day too. But if you actually would do that, you would get to a solution where you cannot assign the forest job before its due time. It's kind of weird. It might not be very clear to see, but these constraints really can make things very difficult to find a good or a feasible or even a near optimal or optimal solution, right? So this is another case. So let's go back to, so the world is full of planning problems. Once you start seeing them, they're everywhere. You go to the airport, security guards needs to be assigned, the gate you go to needs to be assigned, the airplane you get into needs to be assigned. You take a train, the train that comes, the actual train machine that comes to your station needs to be assigned to a planning problem. Where it goes and at which time needs to be assigned in a planning problem. The world is full of planning problems. So in those kind of cases, you can use Optoplanner, which is an open source AI constraint solver, Apache license, sponsored by Red Hat. And today we're going to use that to implement this application, as I said earlier. And we're going to do that on top of the Quarkus framework, which is also an open source platform for Java or even Kotlin development, right? Now, Quarkus is supersonic subatomic. And you might think, okay, that's fancy marketing talk, but I'm going to show you it's supersonic. I'm actually going to show you in a few minutes and then I really show. So what are we going to do? We're going to build this application using Quarkus. We're going to put, there's a REST service on to expose the domain to our client, JavaScript client through JSON. We'll use Jackson for that. And we're going to use JPA Hibernate to store the data in the relational database. Of course, you could pick any other combinations of this. You could say, I'm going to go to a MongoDB or other things like that, but today I'm going to focus on this implementation. So how do you get started with Quarkus? Well, you go to code.quarkus.io, and that will help you set up your project, generate a POM and the directory structure and so forth. So I just want to show that for a minute. So Here's code.quarkus.io. So what I can do here is I can say, okay, I want to have an application. I'll use Maven here, and I want to use, for example, Hibernate. So I add Hibernate with Panache. It's very similar to what Spring has, which is one of the competitors of Quarkus. And you can pick and choose the things you want, right? So you can use add Optoplanner in here. Let's do that, and so forth. I'll take the Jackson implementation, glue code too. And of course, you can add like Jackson, for example. Here we go. Rest Easy Jackson to exposing. And then you click the green this button over here, and it will start. You can download the zip. You can actually look at it first, but you will download the zip. Oh yeah, the internet's off here. So luckily, I've prepared for that. That's good news. So I actually have the application here all implemented a bit already, not entirely. There's no AI in this application yet. I did already implement the persistence part and the rest part, and I'll take you through those code right now. Now before I do, I just want to go a little bit further. I first want to explain a little bit about the domain classes, right? The ones that we'll be working with. So remember, we're assigning lessons to rooms, to time slots, and then we get a solution like that, right? So how does it look like in domain-wise? Well, domain-wise, we have a time slot class, which has a day of week, like Monday, Tuesday, Wednesday, and so forth. We have a room, and of course, it has a start time and an end time, like 8:30 till 9:30. And then it has a room, like room A or room, then there's a room, like room A or room B, which is a separate class. And then, of course, we have a lesson class which has a subject, for example, math or French or chemistry, right, or history, which has a teacher like Marie Curie or Turing and so forth, has a student group like the 9th grade, 10th grade, and so forth. And we're going to have to assign these to a time slot and to a room. Now, the time slot and the room actually start out as NULL, as not assigned, right, because we don't know. Remember, because if we went back here, before we give it to Optoplanner, the room and the time slots are not assigned. That's actually going to be Optoplanner's job, right? So this is the domain. So let's take a look at how that looks coding-wise. So I'm going to use Quarkus Dev. Now, I've said earlier that, that Quarkus is supersonic subatomic, right? I'm not going to focus on the supersonic part when you put it in production. When and with Quarkus, you can compile natively. You can compile your Java code natively and get it started up in 40 milliseconds, etc. Right? Really great for serverless use cases. I'm not going to focus on that today at all, but do try it out. All of the examples, the example I'll be showing today, you can actually download this, you can compile it natively, and you can try that out yourself if you want to. What I'm going to do is I'm going to show you the supersonic part for the developer experience. You make a change in your code, how long does it take for you to see that change in your UI or in your tests and so forth. And that's the Quarkus Dev thing. So what I'm going to do is, I'm going to go to the code here, and I'm going to start Maven Quarkus Dev. And if my live demo goes well, I will not stop this anymore for the rest of the application. So usually I do this in the morning, and this just keeps running the entire day. And you will now see, so over here at localhost there was nothing, but now that I actually started it up, I can do a refresh. I have my JavaScript UI, and there's the code already to load the unassigned lessons from the database. But like I've said, there is no AI code yet, so when I click the green button here to solve it, and where my AI should be doing stuff, I get an error because there is no code behind it. That actually throws an unsupported operation exception. Okay. Now, so Quarkus Dev is running. Now, every time I make a change, I will come back to the browser here, and you will immediately see those changes on screen. So let me go through the code with you, and then actually show you how that works. So, like I said, there's a couple of domain classes, so let me take you through those classes. There's a room class, which is quite simple. It has an ID, a database ID, a long, and a name. Now, we want to put this in the database, so using JPA, we've said, okay, this is an entity, something that actually has a table, a room table in the database. And we've also generate, it also has a database ID, which is automatically generated by the database. Everything else in here is just getters and some constructors and a nice toString. You can, you don't have to do this. I like to do that. Then we have our time slot class, pretty similar. Again, it's something that goes into the database. It has an ID, which is generated by the database. And then it has those three fields I talked about earlier, the day of week, which is java.time, which is java.time enum, like Monday, Tuesday, Wednesday, and so forth. And then, of course, we have a start and end time, again, using java.time. Never, ever use Java util date, right? I guess that's everybody knows that these days. So, and then we have our lesson class. And so in our lesson class, we have, again, we store it in the database. Again, it has an ID. That's the database ID it gets for the table that will represent all lessons. We have our subject, our teacher, our student groups. I've kept it simple as just plain strings. You could actually make those classes and link to those. I didn't want to do this didn't want to add the complexity here. And then we have our time slot and our room class, which is a many-to-one relationship. For those familiar with JPA, this basically means that the lesson class has a foreign key into the time slot table and a foreign key into the room table. And so Hibernate and JPA make sure that that all works out. There's one more class I have that I didn't talk about yet, and that's our timetable. Because I need something to send to the UI. I want to send just one class to the UI with all of my information. And so that's my timetable class, which has a list of all my time slots, a list of all my rooms, and a list of all my lessons. I just gather those up and send those to my UI. Now, okay, how do I read and write to the database? Well, I'm actually using Hibernate Panache. Panache is something, a component within Quarkus to read and write from the database, to have CRUD operations to the database without having to encode those yourself. For those of you familiar with Spring Data, it's it's pretty similar to that. Now, there's two ways to do it. You can add it on your entity itself as a Panache entity, or you can do it more the traditional way using a repository class, and that's the one I've used here. So let me show you that. Here's my entire repository class. So this is a class where I can say, this has a number of methods. Let me show you. If I do this, okay. I forgot this, the shortcut apparently, but here we go. Has a number of methods such as delete, find, get, list, persist, update, and so forth. And this means from now on with this class, I can read and write rooms to the database. And this is my room repository class. As you can see, I just implement the Panache repository interface, and I give it my entity class. And then what Quarkus will do is it will generate all of the code around that, and it will do that at build time, not at bootstrap time. Right? So it will do that when you compile the class, it will generate the necessary code for this. It will not do that at bootstrap time, for example, as at least older versions of Spring did. So then we have our lesson repository, same principle, and we have our time slot repository, same principle. Now, I'm actually putting some test data in the database, and this is using my demo generator here. This is a class which is putting all my test data in the database. So I'm injecting my repository classes here, the ones that the services that I will use to actually write my test data into the database. In a transactional method, I'm listening to the startup event. So this means every time Quarkus starts up, this code will be run. Every time. Even when I change something in my code, Quarkus will restart the entire application and rerun this code for me. I'll show that in a minute. So, what do we have in here? I'm adding some time slots to the database, 10 time slots, 3 rooms, and 20 lessons. And those are the ones, of course, which you see here or over here too, right? You see the 3 rooms here, you see the 10 lessons here, you see the 20 lessons here, and the 10 time slots here, right? So, let's change something. Let's change actually this to JFall. This is the JFall room. Well, actually, we're here in room 6, so let's change that to room 6 of JFall. Okay. Now, if I go back to my application, I've not touched anything yet. Quarkus has not done anything yet at this moment. You still see there room A, room B, and room C here at the top. But when I actually refresh the browser, let me first tell you what will happen. What will happen is the following. The JavaScript, of course, the browser will fetch refetch the page. But Quarkus will notice that a REST request comes in, and we'll also notice that some of the files on system have changed. So it will say, okay, I'm going to make sure I restart the entire project. That means I delete the database, I adjust the database schema, I recall that startup method I have to input all of that test data in my database. And when all of that is done, then the actual code behind, with JSON fetching the information for this is my rooms and this is my time slots will also happen. Let's see how long that takes. I'm going to click the refresh button here, right? And instantly I can see the changes, and you can see room 6 in JFile over there. So how long did that take? Let's ask Quarkus. The live reload took 1.4 seconds, a little over 1 second. It's actually quite slow because this is a slow machine. This is, I think, 5 years old. Usually I have it at 500 milliseconds, half a second. That's how fast the round trip is. This is Quarkus. This is supersonic, subatomic. So let's do that again, because I wouldn't believe this if I would see this. So let's change this to something else. Here we go. We do refresh, and there you go. You can see the changes there immediately. Let's bring it back to what it needs to be, room C, just for clarity. Here we go, we refresh, and we see it again. So this allows you to make changes and immediately see the changes in the effect of the changes on your code. Okay. Now there's one more thing in here. So I've explained the domain classes, I've explained how do you go to the database, I've explained how do you write some test data in the database. So what I do here, by the way, is just call that persist method, where I've just created all of those rooms. And there's one more thing in here. There's the REST service. And I have a simple REST service to expose all of my lessons to the UI in case I want to add or remove lessons. And same for room and time slots. And I have one special one, and that's my timetable resource. This is actually a custom REST method, custom REST thing that I wrote. So what do we have here? First of all, I'm saying the path is timetable. I'm using here JAX-RS annotations. You can actually use in Quarkus also Spring REST annotations if you want to. I prefer the JAX-RS ones. As you can see, I have the database things injected here. And so I have a get method here that when a REST call comes in, a get REST call comes in, it will actually load my timetable, which is a little bit below here. This is my load my timetable. So what do I do in here? I create a new timetable object. I get a list of all of my days of week from the database, all of my time slots from the database, all of my rooms from the database, and all of my lessons from the database. Now, the nice thing is we can make changes in here. So again, just to prove to you, if I first change this to teacher and subject, and I refresh this, then of course these will be first be sorted by teacher. You can see this, Alan Turing first, then C. Darwin, and so forth. So again, we can make any changes here, and those changes immediately reflect in the UI. Now, also notice this is transactional. So I'm actually calling a transactional method from another method in the same class, and the transaction is actually on it. That actually works. Something you will not see will not see often. And this is again because it's not happening at bootstrap time; it's happening at build time. The code changes. Okay. It's time to there's a save method here too in case I have a timetable saved, a times table, and I want to actually persist the links to the rooms and time slots. Okay. Now, let's add some code. Let's start live coding. AI planning optimization. So, what do we need to do? We need to add Optaplanner. I've actually already added the module in the POM already. There's just no Optaplanner code in there whatsoever yet. And in our timetable class, I need to tell Optaplanner what can it change. Can it change the subject of a lesson? No, it can't. It can't decide that math all of a sudden becomes I don't know, history or something like that, right? It cannot change the student, the teachers, and stuff like that. That's all predetermined in this particular use case. We need to tell OptiPlanner what can it change, what can you decide with AI. In this particular case, it's the time slot and the rooms. That's the things that change during planning. OptiPlanner can decide for each room which time slot it is, and for each lesson which time slot it is, and for each lesson which room it is. So again, before planning, these fields are null. After planning, after solving, these fields will be filled in by the constraint solver. Any class that has one or more planning variables needs a planning entity annotation, so OptiPlanner finds it very similar to how any class that goes to the database needs an entity annotation, right? Okay, let's start coding that. Here we go. So I go to the lesson room, right? I'm saying, okay, this is a class that has something that OptiPlanner can change, so I make it a planning entity. Particularly, it is the time slot that it can change. So I'm saying this is a planning variable. This is something that changes during planning, the time slot. Of course, OptiPlanner cannot just create its own time slots, right? So it actually needs to know from which time slots can I pick from for each of these 20 lessons, right? And we actually have 10 time slots that it can pick from for those 20 lessons. So we're going to give this an ID called time slot range, and where we have the list of time slots, we'll actually say, okay, here's the time slot range. And for room, we're going to do the same thing. So we're going to say, okay, this is a planning variable. And we're going to give it we're going to give the range of rooms it can pick from an ID, and we're going to call that the room range, right? So this is what we need to do in the lesson class. Now we need to get that list of time slots and rooms somewhere, but we also need to give something to OptiPlanner. Just here's the whole data set you need to solve, and then because that's the biggest problem for planning optimization. You cannot just assign one lesson and be done with it. You cannot decide one lesson without assigning all of the others. You cannot assign them one by one. You need to assign them. They influence each other, right? So that's why you need to give it as one big data set. So here's the timetable problem. Here's a timetable where we have all of my rooms and all of my time slots and stuff like that. So the first thing we're going to do here is OptiPlanner needs to know, which lesson instances can I change. So we're going to say, okay, this is the lesson instances you can change. This is the property that has the collection of your entities, so the ones you can the lessons you need to assign to times and room slots. And then, of course, to which time slots can I assign? Well, that's this list, this time slot list. So we're going to make that the value range provider, which will provide us that, if you remember from the previous code, that time slot range, right? So if you remember from this code, this said, okay, here's the time slot range. So for each of those lesson instances, which time slots can I choose from the ones that are in this list particularly. And in a similar way, we're going to do that for the rooms, of course, which is then a list of our rooms. Now, the moment that OptiPlanner actually and this particular class, OptiPlanner needs to also make sure, we need to make sure that this class is read by OptiPlanner. This is the input and the output. This is the problem and the solution. It's what we give to OptiPlanner. It optimizes where it assigns all of the lessons and then gives it back to us. But that's also the planning solution. So we need to add a class annotation for that too. Okay. Once OptiPlanner assigned all of those lessons, it's actually going to tell us something. How good is this solution? Right? Is this a good or a bad solution? Is this something that where hard constraints are broken, soft constraints are broken, or not? And we do that it can tell us that if we add a score on this. So we can say, okay, this has a hard soft score. So if none of the lessons are assigned, then there is no score. But once it starts assigning lessons, it will tell us how good that plan is, how good that schedule is, and that's that hard and soft score. So again, we need to tell OptiPlanner, okay, this is our score instance, right? And I'm going to add a getter for that because I want it to be visible in the UI also. So let me just add a getter for the score too. Okay, so now OptiPlanner understands our domain model. It understands, okay, I need to assign lessons to time slot and to rooms, but it doesn't understand our constraints yet. Can I put 2 lessons in the same room at the same time? Yes or no? It cannot. It doesn't know that yet. So we're going to add some constraints. So I'm going to add a constraint provider. I'll get back to that in a minute. I'm just going to add no constraints for now, but I'm going to add, I am going to give it a constraint provider. So it does say, okay, it understands that there are no constraints. So here we go. We say this is a constraint provider, and I'm going to give it a new, an empty list of constraints, right? So currently there are no constraints, which basically means Optiplanner, you can do what you want. Yeah, okay, let me fix that. Maybe, here we go, that's a typo. Okay, so that's fine. Let's start again. So you can see that Quarkus Dev is still running, right? I need one more thing to do. When I click that in the UI, when I click this green button and nothing happens, right, this one, it actually goes to this method over here on the timetable resource. And you might have seen that on the solve method. That's what happens when we click that green button. And that's where we have the unsupported operation exception. So here we actually want to solve the problem with Optiplanner, right? So what are we going to do? In Quarkus, we're going to say we're going to inject something that can help us solve this problem, and that's called a solver manager. And it's a solver manager for our timetable. So something we can give the solver manager, here's a timetable, it will solve it for us and will give it back to us. And it can actually handle multiple timetables of different schools, for example, in parallel and so forth. And it wants to know what is the problem ID for each of those. So we can choose any type of problem ID, but here I'm going to use an ID of a long, just for simplicity's sake. So now I have a solver manager instance that gets injected here. So when we click the green button and we go to this solve method, I can now say, instead of throwing an exception, I can now say, okay, solver manager, please solve. And I'm going to use something called solve and listen. Please solve my problem. So what's the difference between just solve and listen? Solve is good for batch jobs. You solve it, and when it's finished, you can do something with the results. In this case, I actually want, every time there's a new and better solution, I want to immediately show that in my UI, so that the UI shows my improvements as Optiplanner is solving longer. The more time we give it, the better the solution, right? So I'm going to say, okay, this is, I need to give it a problem ID, a job ID. I'm just going to hard code it to 1 because there's just one. We're only going to solve one problem today. And then given that problem ID, that 1L in this case, I need to load my problem. So I'm going to load my timetable. And then given my solution, I need to save that. So I need to add the right of that method too. So what does this do, the solve method? It says, okay, please solve a problem for me. Here's where you can load the problem. Here's where you can load the problem, and here's every time you find a new and better solution, you can save it there. So for one problem, we will save it multiple times. Every time we find a better solution, by solving longer, it's going to save that into the database. So let's, and we can also limit the amount of time we want Optiplanner actually to solve, or we can just let it run forever and terminate asynchronously. In this case, I'm going to add a property to actually just run it for 10 seconds. So here we go. This is the spend time property. I'm going to say you can solve for 10 seconds, right? And let's go to the UI. Let's try this out. Remember, we have no constraints. Anybody got an idea what will happen? So we're going to have Optiplanner assign these 20 lessons to these 3 rooms and 10 time slots. Let's click the solve button. Here we go. Optiplanner starts doing that. There's a 2-second refresh in the UI, so that's why it takes 2 seconds to actually show that solution. You can see what happened. It assigned all of the lessons to room A at the first time slot. Because there's no constraints, it's all fine. Not exactly what we want, right? Yeah. Okay, let's see if we can fix that. So let's talk about constraints. There's 2 types of constraints, hard constraints and soft constraints. Hard constraints must not be broken, soft constraints can be broken. A good example of a hard constraint is you cannot put 2 lessons in the same room at the same time, and you can definitely not put all 20 lessons in the same room at the same time, right? There's also soft constraints, like for example, a teacher does not like to have a lesson in the morning, a lesson in the evening, a lesson the next day at 9 o'clock, and a lesson very late in the evening, right? They want to have a compact schedule. That's typically soft constraints. So let's go through all of those. Let's go through some of those. So now the easiest way to implement this would be like this, and you can actually do that in Optoplanner, but it has a downside. But let me go through this. The easiest way to implement the room constraint would say, okay, I'm going to go through all of my lessons. Lesson A, I'm going to go through all of my lessons again. I have two different, and of course, if they're the same lesson, I actually not show that in this code for simplicity. But if those two lessons have the same time slot and they have the same room, then I break a hard constraint, right? Don't do that. Then we hit Optoplanner on the head and tell them don't do that, right? So what's the problem with this code? Can anybody? So it's a bit hard to see what's the problem with this code, but it's not incremental. What does that mean? That means when those algorithms who need to go through tens of thousands or hundreds of thousands of different solutions per second, right? Every time. For every one of those solutions it generates, it needs to know the score. And for every one of those, it needs to go through this double for loop. That's too expensive. That's way too expensive. So when the room of the math lesson changes, it also checks if French and chemistry still use the same room. But French and chemistry didn't change. That's a waste of time, right? So when one room changes, when it actually checks every other room with every other room again too, that's a huge scalability difference. If people who are familiar with the big O notation, that's a very different big O notation. That's not what we want. There's a better way of doing things. The problem is writing that better way is where you do deltas. So what's the delta? You figure out, okay, room A changed. Let's take a look at how many of the constraints could be infected by that. Writing deltas is the best way to go insane. I've tried it. It is by, you know, we have a couple of implementations there. They're hard to maintain. They're hard to write, and they drive people insane. So don't do that. So can we have our lunch and can we have our cake and eat it too? That's why we invented something called our Constraint Streams API. It's very similar to Java Streams API. It has a few additional properties. That's why we couldn't just reuse the Java Streams API. But let me show you how it works. So we're going to write a room conflict constraint, right? So here we go. We're going to create a method for that. So this method will create our room conflict constraint. And so using our constraint factory, which is the thing that can create the streams for us, we're going to say, very much like an SQL query, I'm going to say, you know, select me a lesson, give me a lesson, right? So it's going to run that for every one of the lessons, right? And then we're going to say, very much like the first for loop, and then we're going to say, okay, join this with any other lesson. Okay, sometimes code completion is a bit annoying. So here we can see, I'm taking a lesson, give me any other lesson, right? And then let me just write the rest of the part. We're going to penalize this as a room conflict. And we're going to penalize this as a hard constraint. So we're going to say hard soft score, 1 hard. Here we go. Now, this isn't good, right? Now we take any two lessons, right, and we penalize them. It's not any two lessons. It's lessons that happen in the same room at the same time. We could use a filter in here where we can, you know, with a by function, but that's not that efficient because it is going to be incremental, but it's not going to use hash tables. And that's another thing you want to use. You want to use hash tables, hash lookups. Again, that's another reason why you wouldn't want to use these for loops. Let's use that, and just like in SQL, what you would do is you would say, okay, I want to do, you know, it's going to use indexes underneath, right? So what we're going to do is we're going to say, okay, joiners, if for this lesson, for these two lessons we've just selected, if they have the same room, and also if they have the same time slot, then we have a problem, right? So anytime we have two lessons with the same room and the same time slots, we have a room conflict. Okay, let's jump to our UI. Let's go over here. Let's click refresh. look, I made a mistake somewhere in my code. The missing return statement. That sounds pretty obvious here. So there's no return statement here. Here we go. Live coding is always fun. And here we go. So let's click. We still have our lessons unassigned. Let's click the solve button. What will happen now? Well, we've just solved our room conflict constraints. All of the lessons are never in the same room at the same time. Do you think this is a good schedule? What's wrong with this schedule? There's something very, very wrong with this. Yeah, let's take a look how it looks for the teachers. Let's start with that. This one looks good. Well, okay, here, Marie Curie. Hopefully she can be at 2 places at the same time, because Tuesday, 9:30, she has to teach both French and both physics to do different things. So that's not a good thing, right? And similarly, if you look at by students, we're probably going to see some issues there too. As you can see here, some students need to take 2 lessons at the same time. Again, not ideal. So let's actually fix those too. So what we're going to do is we're going to say, okay, we're going to add a teacher conflict. Here we go, teacher conflict. And there we go. Let's generate that method. And very similar, what we're going to do is, okay, constraint fact. I can actually copy this one, right, for easiness sake. So let me just explain. When we have a lesson, when we join with another lesson, it does need to have the same room. It needs to have the same teacher, right? When we have 2 lessons that have the same teacher, that they are using the same time slot, then what we call a teacher conflict, and again, it's a hard constraint. Optoplanner must never, ever, ever do that. That means hard, right? And so let's try that out. We refresh. We click the solve button. Looks good for room still, because we still have that constraint. Looks good per teacher now too. Okay. And then when we go back here, well, of course. And then if you look per student group, we still have that issue because we still don't have that constraint. So again, you go back over here, rinse and repeat basically, right? So we say, okay, give me a student group conflict constraint. Very similarly. So again, we go from give me a lesson, select for any lesson, join with any other lesson. If they have the same student group, and they're happening at the same time, that is a bad thing. This is a student conflict then. Student group conflict. And of course, if we go back to the UI, what we will see, if we solve it now, we get our first feasible schedule, right? Again, all the rooms are fine, as you can see. All the teachers are fine, as you can see. All the student groups are fine, as you can see. Solving this by hand is non-trivial. It's far from non-trivial. This is the reason why the beginning in September when you went to school, it was typically hard to get. It typically took a while before the schedule stabilized, right? Add in some extra fun stuff like Marie Curie cannot work on Mondays, and you get more constraints you can start adding. Typically what we see is that 80% of the constraints that we see with business are always the same. Everybody has, every school has the room conflict constraint. There's always 20% of the constraints that are different, right? And that's why you want to be able to add constraints, any type of constraints, very easily, like I've just shown you, right? This includes fairness constraints that you want to make sure that for example, because there's still a bunch of constraints missing here, right? So if you look at the full example in Optoplanner Quick Starts, what you will see is there's constraints in there to make sure that the teachers have a compact schedule, right? That's a soft constraint, but there's very few violations of that. You can see here this is not a really good schedule for Marie Curie, right? She has a gap lesson here, she has a gap lesson there. If you add that constraint, those things actually go away. But okay. So if you want to get started with any of this, how do you get started with this? You go to optoplanner.org. There's a link to the Quick Starts repo on GitHub. You clone this one, then you go into the repo itself. And you take the school time tabling example and you run Maven Quarkus dev on it. We have use case. Let me just show you. If I have internet here, not much. Okay, no internet. Okay. try this out yourself, and you will see in about in a minute or two you will have this running this example running on your computer, and you can actually start messing with the constraints to get a different form. I've already shown code.quarkus how you can get started there. So if there's any questions, I'll happily answer those now. Yes?
Yes, I saw in the constraints that you were not checking explicitly on identity.
Yes, I should. I did that because due to lack of time. But let's do that. It's a very, very good question. So what you should be doing also is, because, yeah, I cheated. Let me show you how I cheated. You can see here in the logs that Optoplanner was solving. And you can actually see it says here, it's maybe not that clearly visible, is there 60 hard constraints broken. That's actually those lessons that match with themselves. So that's not a good thing, right? Why 60? Well, there's 3 constraints, so and there's 20 lessons, so 3 times 20 gives us 60. So if you want to do that right, what we should be doing is there's a couple of ways to do it, but let me do it on the room constraint first, right? So what you can do here is you can do joiners. There's more than just, you can check identity, right? So you can do it with the filter, right? So you could do this filter lesson 1. So lesson 1. Here we go. Lesson 1, lesson 2. All right, and you can do something like this. Lesson 1 differs from lesson 2, right? And so when you run this, let's do that. Oh, sorry, let's do that. Here we go, let's solve that. Here we go, and let's look at the log. And you will see it will now go to -40, see? Yeah, there's a problem with that though. When you actually do have a hard constraint broken, it will match it. For example, math and French are at the same time. It will actually say math and French are at the same time, but it will also say French and math are at the same time. So A and B and B and A. And the way you fix that one, and that's what you will see in the full implementation, by the way, is not with a filter, but with where you say, okay, joiners, less than lesson get ID. So this will basically make sure that the IDs are different, and also that the first lesson has a lower ID than the second lesson, right? And that way, if you run this, let me just try it out. If it still works, here we go. Notice Maven Quarkus Dev has not restarted yet. It still works. I can do 100 hot deploys. This is not hot deploys because the whole thing restarts, right? This is not instrumentation. The whole thing actually restarts every time I press the refresh button. But no out of memory errors or things like that, right? And so when we now look at it, it's still okay, as you can see, it's still -40, right? And we can do the same trick for the others to really bring those hard constraints to 0, which you want, of course, in a real full implementation. Any other questions?
How do you set the score?
Good question. So actually, when I get it back here, so I can show that to you. So when I get it back here in the timetable resource, let's put it in the save method here. I can just do, you remember on the timetable I had a score element, a score field. So I can do, so remember I wrote this, right? This getter, I added this, as you can see. This is that score. So now actually in this, here I have the score. So I could do, if I wanted to, I could do a system out of that, like this. And then let's do that. So JFall, here we go. Right. And so you get the score, and you can actually also ask, give me the hard score as a number, as an int, give me the soft score as a number. You can ask, is it feasible? That means that the hard score is actually 0, or and so forth and so forth, right? You can choose for more than just hard and soft score, by the way, but that's going beyond the scope of this presentation. When you want to do really, really crazy things. I always figured people don't need more than hard, medium, and soft score. Medium is when you need 3 levels. And then I saw customers using 20, and I still don't understand why. 20 levels, but we support it. And users, yeah. And then We can also, right now when you do here you can see that the score is not on here yet, but we can actually, you see in the full example it actually shows up there. The reason it doesn't is because it gets the whole timetable from the database. So then you need to calculate the score without actually calling the solver, and you can do that too, and the example shows that. Any other questions? Yeah, I think we're out of time. Thanks for listening.